Write it climate. Climate is for long period. What is this long period? Climate is for long period. What is this long period? Climate. Long period, right? Soil. Long period. Then, what else apart from this? Climate is for long period. Online, am I audible? Am I streaming fine? Am I streaming fine? Yes, fine. So climate is for long period. What does this long period stands for? What is that years? Is it 1 year, 2 year, 10 years, 15 years, 20 years, 12 years? Why 12 years? Why? That is a 12 months, right? What does the climate stands for? How many of years? How many years? And what is the weather then? What is the weather condition? Day-to-day behavior of atmosphere or day-to-day updates about atmosphere is called as a weather or weather phenomenon, which means weather stands for one day, 2 day, or 3 days, whereas a climate stands for 31 years, a minimum. So climate stands for, climate is a weather average of a long period that stands for 31 years minimum, according to World Meteorological Organization. So according to WMO, climate, if you want to say that this is the climate or climate is changing, you need to have an at least of a 31 years of weather data with you. So that is the minimum requirement. So climate stands for a long-term atmospheric phenomenon, and that long term is 31 years. Whereas the weather stands for day-to-day atmospheric phenomenon. Day-to-day atmospheric phenomenon, which means there is a weather counts days, whereas a climate counts 31 years a minimum, which means there is a temporal difference between both the terminologies. Temporal difference means time-based difference. This stands for a day, this stands for years. That is the temporal difference between weather and climate. Temporal difference between weather and climate is one weather counts days, whereas a climate counts years. Apart from temporal difference, there is one more difference. Spatial difference is also there. Spatial difference. Apart from this, there is a spatial difference. Spatial difference. What is a spatial difference? What's a spatial difference? Spatial difference talks about the geographical area or the space, which means if it is a climate, we are talking about the climate of Asia, climate of North America, climate of India, climate of East Asia, climate of West Asia, climate of Africa, which means it holds a larger geographical area. It is whether it is North America, Africa, whether it is India or Asia. Climate stands for a vast geographical area, whereas the weather stands for Western Delhi, the weather condition in Western Delhi, the weather condition in Western Chennai, weather condition in Cochin, weather condition in Kolkata, which means that focus only very small geographical area. So this is the second difference. So weather stands for a small geographical area, which means a small city, a small town, a part of a district. So that is the second difference. So between climate and weather, there is a both spatial as well as temporal differences there. Spatial differences, Weather talks about a very small area, small geographical area, whereas a climate talks about a vast geographical territory. Fine. Weather is highly variable. Weather is highly variable. Weather is highly variable. And its elements are interdependent. And the elements are interdependent. The elements are interdependent, which means what are the elements of weather and climate? One is temperature. Second one is air pressure, moisture, winds, different types of precipitation. All these are some example of weather elements. They are interdependent. Whereas a climate is an average of weather condition. Climate is an average of weather condition. Average of weather condition for a minimum of 31 years. Talks about the temperature condition of a particular area for 31 years. It talks about the pressure, wind system, rainfall pattern of a particular area for 31 years, a minimum. Which means we can say something like this: the northern part of Gujarat was experiencing or have been experiencing continuous rainfall in the month of June, July, August for the last 100 years. So that is the average that we consider in climate. So what are the differences between both the terminologies? There are two differences are there. One is spatial, second one is a temporal. Spatial difference talks about the geographical area, whereas a climate talks about, when a geographical area, spatial aspect, climate talks about a vast continent or a part of the continent or a part of a country, whereas a weather talks about a part of a city or a part of a town or a small geographical area. Apart from the spatial differences, there is one more difference is there, that is a temporal difference. What is a temporal difference? Weather talks about day-to-day atmospheric behavior, whereas a climate talks about a large area, which means large span of time. That means a minimum of 31 years. That is according to World Meteorological Organization. So this is the basic understanding between weather and climate. So you can talk about how is the weather today, or you can ask how is the weather today, or you can talk about today's weather is a bit fleecy or it is very, very harsh. So that is the correct usage. Don't talk like this. Today's climate is pretty bad. It's not right. Yeah, fine. All right. So let's get into our main area, that is an atmosphere. What is atmosphere? What is atmosphere of Earth? What is atmosphere? Which means Earth is consisting of three basic realms. One is a realm which is made up of different types of gases. Second one is made up of water. Third one is made up of rocks. We can call a realm that is made up of gas as atmosphere. One that is made up of rocks, you can call it as a lithosphere. One that is made up of water, you can call it as hydrosphere. And when three of these spheres come together, that forms biosphere. That is a part of the biosphere. So for your batch, this part is already done. The lithosphere is already done under geomorphology. Second one is made up of gas, that is atmosphere, that we'll be discussing under climatology. This one will cover under oceanography. And this is a very small area under geography. That is a biogeography. The rest of that part will be dealt under environment, biogeography, environmental things. So our domain of discussion is atmosphere. What is atmosphere? It's a mix of gases. Fine. Anything else apart from that? Greenhouse gases. What is greenhouse gas? Carbon dioxide is an example. What is it? Which absorbs heat from the Earth's surface. Fine. All right. So atmosphere, the basic understanding is it's a gaseous envelope that surrounds the planet Earth. It's a gaseous envelope that surrounds the planet Earth. It's a gaseous envelope that surrounds the planet Earth. Which means this is the Earth, body of Earth. Over that body of Earth, you can find there is a layer which is made up of different types of gases that surrounds or envelope, that covers the planet or wrap around the planet throughout. This is called as, this blanket which is made up of gases is called as an atmosphere. What is the height of atmosphere? Till what height you can expect atmosphere? 800 kilometers, 80 kilometers. $2,000. No. Which means this is the place we all are standing. From here onwards, atmosphere starts. And my question is, up to what height you can expect atmosphere? Here we have the atmosphere. You can inhale and exhale the air, which is a part of the air, which is a part of the atmosphere, right? Which means till what height I can expect this body of air? What's the height of Everest? No, 8,840. 40? No. 8,848. Approximately, it is measured around 1950s. Till now, Himalaya is growing, Everest is also growing. So sometimes it may be around 8,860 or something. But on an average, it is 8,848, which means this is 8.8 kilometers. We have atmosphere there also. So tell me, what is the height? What is the upper limit of Earth's atmosphere? Once again, 800 to 1,000 kilometers. 800 to 1,000 kilometers. All right. $1,240 kilometers. 800 to, one value was 800 to 800 to, and 800 to 1,200 kilometers. Somebody was mentioning about 80 kilometers. Then, anything else apart from this? Any values other than this? Any values? What is the upper limit of atmosphere? Online, you can also mention. What is that? That is Everest, the Valley of Everest. Yes. What is the upper limit of Earth's atmosphere? What is that? 80 kilometers. What is that? Thermal? Kremlin line. Fine. No. So, Earth's atmosphere is not having a definite boundary. There is no definite upper boundary set, but it has a lower part. That is the Earth's surface or the sea level. That is a starting point. If there is a depression, if there is a trench, there also you can find the atmosphere will be penetrating, which means atmosphere has a starting point, but that ending point is not defined clearly. You can say that there is Earth's atmosphere at 5,000 kilometers. Earth's atmosphere is there at 6,000 kilometers. It is there at 10,000 kilometers. But it is not like as we see the atmosphere at the surface. It is a highly rarefied atmosphere. But technically it is there. For all our scientific purposes, we have set a limit for the active atmosphere of the planet Earth. That is 480 kilometers. This is the boundary of the active atmosphere, 480. 480 is the boundary of the active atmosphere, which means that does not mean that beyond 480 there is no atmosphere. It is there, but the air is highly rarefied. So 480 is considered as the limit of active atmosphere. You are talking about a number 80. What is that? 80. Yeah. Anything else? Yes, atmospheric pressure reduces exponentially after that. Fine. So this is 480 kilometers considered as the upper limit of the active atmosphere. So that is the upper limit. And next is why this atmosphere is staying here. Why it stays there? We are able to inhale gases because the atmosphere stays here. What is the reason behind this? Why it is staying here? Why it is not jetting out? Why it is not going out? Because something is pulling it towards the Earth's surface, the gravity of Earth. So the atmosphere stays there around the planet because of the gravity of Earth. Because the gravity pulls the atmosphere towards the surface. That's why it stays there. Otherwise, all these individual gases might have escaped from the planet. So the gravity is the reason behind the wrapping of the atmosphere around the planet. That is the reason why it stays here. This is the particular area. And the atmospheric pressure is maximum at the lower part and it decreases with increase in height. So Earth's gravity pulls it back to the surface. That's why it stays there. About 97% of the air is concentrated within 29 kilometers. About 97% of air is concentrated within 29 kilometers. About 97% is within 29 kilometers, which means here we are living here. Within 29 kilometer, you can find 97% of the air molecules, which means the air pressure is maximum at the lower part of the atmosphere. Air pressure is maximum. Air pressure is maximum at the lower part, and it decreases with the increase in height. Atmospheric pressure is maximum at the lower part and it decreases with increase in height. It forms a protective boundary between the biosphere and the outer space. Boundary between the biosphere and the outer space. So the present day atmosphere is a product of continuous volcanic eruptions, hot springs, ejection of gases from hot springs, chemical breakdown of solid matter, and the redistribution from biosphere. Which means right now we are living in the secondary atmosphere of the planet Earth. We had an atmosphere which is called as a primary atmosphere, which is already lost. And right now we are living in an atmosphere that is evolved very slowly. That is a part of this atmosphere is called as a secondary atmosphere. We have the maximum concentration of nitrogen, oxygen, argon, and carbon dioxide. Initially, the primary atmosphere that we had was the major composition was hydrogen and helium. So right now what we are inhaling and exhaling is the secondary atmosphere. Fine. All right. Evolution of atmosphere. Evolution of Earth's atmosphere. Atmosphere basically went through three different stages of evolution. Three different stages of evolution. The first stage is nebular accretion. And associated outgassing process. Nebular accretion and the related outgassing. Second one is continuous volcanic eruption, which is called as degassing. The third one is emergence of life and its influence. emergence of life and its related development, or emergence of life and its influence. So these are the three different phases or stages of the major stages of evolution of Earth's atmosphere. One is a nebular accretion and outgassing process. Second one is called as a volcanic eruption, called as a degassing. Third one is called as emergence of life and its influence or related developments. So what is the first stage? Nebular accretion. The planet Earth is evolved from a cloud of dust particle which was scattered in the space. Planet Earth is evolved from a cloud of dust which was scattered in the space. A cloud of dust which was scattered in the space, which was consisting of different sized materials. Large rock fragments was there, finest dust particle was there, which are generally called as a cloud of dust, that is a nebula. So the planet Earth is evolved from a cloud of dust particle which is called as a nebula. So the planet Earth is evolved from a cloud of dust particle which was scattered in the space, which is called as a nebula. The materials within this nebula started accreting or contracting and solidifying, which means these scattered materials got attracted against each other and they started colliding with each other and they started building the present day Earth like this. So they got an attraction, the dust particle which is already there in the nebula, and they started colliding and contracting into a single body. That's how the planet Earth was evolved. So at this time, in the beginning, the Earth was a hot rotating body. It was not as a solid as we see right now. It was a hot, one molten body. It was evolving like this. And there were different particles were there with varying densities. There were materials like iron was there, nickel was there, silica was there, alumina was there. All those different elements with varying density was scattered here and there in this particular body of nebula, body of protoplanet. So what happened afterwards? It was in liquid stage. Since it was in liquid stage, all those elements, all those particles started segregating according to their densities, which means the denser iron and nickel started going towards the center of Earth. The lighter silica elements started coming out towards the surface. Alumina started layering out towards the surface area. Likewise, we have got different layers of Earth with varying densities. This is what the nebular accretion says. Initially, the planet Earth was consisting of different type of materials, which was evolved from a cloud of dust, and these particles which was there a part of the dust started accreting, colliding, and they created a molten ball that is a proto-planet Earth. And within that molten ball, different type of materials were there with varying densities. They started settling within this body of Earth according to their densities. And the densest elements started coming towards the center, and the lightest elements started settling in the outer areas. And this is the stage of, the first one is, this is the stage of nebular accretion or outgassing. And within this materials, within this material, there were trapped gases were also there. Within this materials, there were some trapped gases were also there, which means there were some amount of hydrogen was there, helium was there, all these things was there. Which means iron and nickel is the densest. They came towards the center and settled at the center. Alumina and silica were lighter. They started coming out. These hydrogen and helium is still too lighter, and they started coming out from the solid body of Earth and created a separate layer around the planet. This became the primary atmosphere with the domination of hydrogen and helium. Got it? Fine. So everything started from a cloud of dust, which was consisting of different types of rocks, dust particles. There were hydrogen was there, helium was there, different types of things was there, and they started colliding each other. They created a hot molten body of a planet, proto-planet of Earth, and the trapped gases started coming out, and they layered around the planet because they were the lightest among the materials within the body of Earth. The densest material sank towards the center and created then liquid iron and nickel created the core of Earth. Then silica, aluminum started coming out towards the surface. And among these materials, the lightest hydrogen and helium came out and created the outer layer that we call it as a primary atmosphere. So right now we got the primary atmosphere. It was staying around the planet, which was dominated by, can you see the color or should I change? Yeah, hydrogen and helium. This atmosphere was the primary atmosphere. What is the age of our planet? Age of our planet? Around 4.6 billion years. So Earth is there and a layer of gas was created which has a domination of hydrogen and helium. We started calling it as the primary atmosphere. So it was there like this. So what happened is at that time, sun was very active. The solar activity was very violent at that time. Sun was very active. And what the sun did during that phase of the evolution? Sun was here. From the sun, there is a lot of charged particles started coming out towards the different planets. There are planets like Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, all these planets were there. And from the sun, a huge amount of solar flares or solar wind started ejecting out and they approached the planet Earth. And they started blasting the primary atmosphere of Earth away from the planet. A huge volume of solar flares or solar wind came from the sun and they blasted the primary atmosphere, which was dominated by hydrogen and helium, and the planet Earth has lost its primary atmosphere there. So that incident was the solar wind blast. It blasted the primary atmosphere of Earth. Solar flares or solar wind blasted the primary atmosphere of Earth. And Earth became like naked without an atmosphere. After that incident, Earth became like naked without an atmosphere. Any doubts still here? No, fine. So Earth lost its primary atmosphere right now. What is next possible development? What is the next possible development? We have discussed about nebular accretion, outgassing has done. That outgassing and nebular accretion and outgassing resulted hydrogen helium dominated primary atmosphere. Solar flares approached planet Earth and blasted the primary atmosphere. Second one is the process of volcanism. So after the solar flare, Earth's primary atmosphere is completely lost. And after that, what happened is, within Earth interior was very active at that time. There were a lot of nuclear radioactive elements was there inside the planet. Inside the planet during this time, a lot of nuclear radioactive elements were there, like uranium, thorium, all these elements were there inside the planet, which came from different part of the space and got settled at different depth of the planet. They started the process of radioactive disintegration. They started the process of radioactive disintegration, called as a nuclear fission. The elements like uranium and thorium started a process of nuclear fission. Nuclear fission. Nuclear fission. Nuclear fusion is that is taking place in the sun, and here it is a nuclear fission. Nuclear fission is taking place below the Earth's surface. So enormous amount of heat energy was generated within the planet Earth. Enormous amount of heat energy was developed inside the planet. Heat energy was developed inside the planet. Which eventually resulted a molten outer core, a molten outer core, a molten outer core, which started its convective circulation, around the solid inner core. Around the solid inner core. Which means right now planet Earth got a solid inner core which was surrounded by a molten outer core, and that there is a continuous circulation, convective circulation is taking place, and this has resulted the formation of geodynamo inside the planet. A dynamo effect is created inside the planet. This has resulted a dynamo effect inside the planet. That is called as a geodynamo. This geodynamic effect has resulted. This geodynamic effect has resulted the formation of magnetic field around the planet Earth. The formation of magnetic field around the planet Earth. Just like an apple. Earth is here and a magnetic field of the planet Earth got evolved. This property of Earth for having a magnetic field, it's called as a geomagnetism. So right now we got planet with magnetic field. What is the advantage of having a magnetic field? Hereafter, yes, exactly. Hereafter, if the solar flares are approaching the planet Earth, the solar flares can come here, but the planet Earth will be protected by this magnetic field. This solar flares or large-scale solar winds, when it's trying to blast the Earth again, this magnetic field causes a deflection of this solar flares like this, which means they are there to protect the planet after their formation. So the magnetic field is a protective layer around the planet to protect it from the solar flares. Because of the presence of magnetic field, the solar flares coming out from the sun, are deflected towards the poles, rather than hitting Earth's atmosphere, or rather than hitting Earth directly. Atmosphere is not there right now. Rather than hitting Earth directly. Here comes the second phase of evolution, the phase of degassing. The phase of degassing. Phase of degassing. So right now, the planet Earth is having a magnetic field to protect it from the solar flares. And as I mentioned, the interior of Earth was very active during this time. That has resulted continuous volcanic eruption on the surface. For millions of years or billions of years, there were continuous volcanic eruption was taking place from the interior of Earth. Continuously, different types of material started coming out. Molten lava started coming out, different types of water vapor coming out, different types of gases, ash, all these things started ejecting out from the interior of Earth. A lot of things started coming out. The gases that were trapped inside, the gases that were trapped inside, started coming out through a series of volcanic eruptions. Through a series of volcanic eruption. The major gases were carbon dioxide, nitrogen, and water vapor. Major gases were carbon dioxide, nitrogen, and water vapor. Probably that atmosphere was consisting of water vapor 60 to 70%, carbon dioxide 10 to 15%, nitrogen 8 to 10%, nitrogen 8 to 10%, and other sulfur compounds. Huge amount of water vapor, got pumped into the atmosphere. They condensed and created a dense clouds and resulted dense clouds and resulted heavy long-standing rainfall for millions of years. Continuous rainfall. So it was rain falling for millions of years. So carbon dioxide, which got dissolved in the rainwater, and got accumulated within the ocean floor, which eventually led to the formation of carbonate rocks. So I'll summarize. Everyone started from that a cloud of dust particles called as a nebula. The particles were in different sized, and they got attracted against each other and collided with each other and created a prototype of planet Earth, which was having a high temperature and molten materials. And that was consisting of different types of elements with varying densities. There were alumina, there were silicon, there were magnesium, iron, nickel, all these things were there. Apart from that, there were gases were also there. And during this phase, since they are in molten state, all those elements started settling according to their densities. The densest iron and nickel started sinking towards the center, and the lighter elements of silica created another layer above that, and alumina created another layer above that. And the lightest among this, that is the gases like hydrogen and helium, started coming out, and they created their own layer above the solid surface. That became the primary atmosphere, which had a domination of hydrogen and helium. It stood there for millions of years. And what happened is, after that, solar flares came from the sun and blasted the primary atmosphere. And Earth lost its primary atmosphere, and it became a naked planet. And during this time, Earth's interior was very active. There was a lot of radioactive elements were there, like uranium and thorium, and they created an excess amount of heat inside the planet, which made the center of Earth, that is the outer core, in a molten stage, and that started circulating around the solid inner core. And this circulation of nickel and iron around a solid iron and nickel created a dynamo effect inside the planets, and that has resulted the formation of a magnetic field around the planet Earth, which started protecting Earth from other external attacks, which means the solar flares. So once this magnetic field was created, it is there to protect us from the solar flares. So this was the protective boundary. And after that, what all things happened inside the planet? There were a lot of radioactive elements. They started enormous amount of volcanic eruption. When a volcano erupted, there were a lot of materials like pyroclastic materials. There were solid materials were there. Rocks will be there. There is a molten lava will be there. Gases will be there. Sulfur compounds will be there. Water vapor compounds will be there. So it started coming out into the outer part of the Earth, which means away from the surface. That stage is called as a degassing stage. And that has resulted the formation of a secondary atmosphere of Earth with a domination of water vapor, carbon dioxide, nitrogen, then sulfur compounds. This was the composition. And these water vapor, which was abundant in the ejection, started condensing into dense clouds and resulted heavy, long-standing rainfall, which washed out some of the amount of carbon dioxide from the Earth's atmosphere, and all those carbon dioxide got settled inside the bottom of the ocean. They created the carbonate rocks in the ocean floor. Fine. And this is how the story of Earth or atmosphere goes. So this is how the secondary atmosphere is created in the planet. But within that list of gases, you cannot see oxygen. But we have oxygen right now. From where this oxygen came from? from where this oxygen came from. Initially, there was a concept like the water vapor which is coming out from the volcano will react with the sunlight, and a photo dissociation took place and created the oxygen. But that concept was rejected, and the credit of formation of the oxygen inside the Earth's secondary atmosphere goes to the cyanobacteria, which means life came in the planet Earth before oxygen. So that credit goes to the cyanobacteria. Fine. The source of oxygen was the cyanobacteria. And then the green plants. And photosynthesis was considered as the source of oxygen. Photosynthesis was considered as the source of oxygen. So this is how the secondary atmosphere evolved. We are living right now, we are living in the secondary atmosphere. Any doubts till here? Clear? We discuss about weather, climate, evolution of atmosphere. Right now we are in secondary atmosphere. Next part of the discussion is composition of atmosphere. Composition of Earth's atmosphere. What all things are there in the atmosphere of Earth? Composition, components, dust particles are there, water vapor is there, different types of gases. Only these three things. Ice crystals, right? Then Earth's atmosphere is composed of different types of gases, dust particles or aerosols, water vapor, ice crystals, pollen grains, and other microorganisms and bacteria. So different types of things are there in the planet's atmosphere. So we'll discuss about the gases first. Gases. Which is the predominant gas in the dry air? Which is the most predominant gases by volume in the dry air of the planet Earth? Nitrogen. When we consider dry air, there we are eliminating water vapor. So by eliminating water vapor, the most important component is nitrogen. 78% of the Earth atmosphere is consisting of nitrogen. 78%. Which is the second most important gas by volume? What is the order of the gases based on their volume? First one is nitrogen, second one is oxygen. 21%. Third one is argon. 0.93%. Fourth one is carbon dioxide, 0.03%. So these are the 4 most predominant gases of the Earth's atmosphere based on their volume. Nitrogen 78, oxygen 21, argon 0.93, and carbon dioxide 0.03. Which is the most predominant greenhouse gas within a dry air? It is the carbon dioxide. Nitrogen and oxygen altogether made up of around 99% of the Earth's atmospheric gases. Which are the important greenhouse gases? Carbon dioxide, methane, right? Important greenhouse gases. Their global warming potential, you can write it in a table. Important gases, global warming potential, their lifespan. Greenhouse gases, their global warming potential, their lifespan. First one is carbon dioxide. This global warming potential stands for 100 years. Global warming potential, 100-year time horizon. Within that 100-year time horizon, global warming potential of carbon dioxide is considered as 1. An average lifespan of carbon dioxide in the Earth's atmosphere is around 100 years. Around 100 years. Methane, second one. Global warming potential of methane is 25 times than carbon dioxide. 25 times than CO2. (25 times than CO2). Lifespan is methane lifespan. What is the lifespan of methane? 12 years. Once it is ejected or emitted into the Earth's atmosphere, it can stay there for 12 years. But with a potential of 25 times than the carbon dioxide. It is highly harmful than carbon dioxide. So lifespan is 12 years. 12 years of lifespan. The third important gas is nitrous oxide. Nitrous oxide. Nitrous oxide is having a potential of 265 times than carbon dioxide. 265 times than carbon dioxide. 265. With a lifespan of 121 years. With a lifespan of 121 years. Next is chlorofluorocarbon 12, CFC 12. Chlorofluorocarbon 12, CFC 12. Global warming potential is 10,200 times than carbon dioxide. Lifespan is 100 years. Sulfur hexafluoride. Sulfur hexafluoride. Global warming potential compared to CO2 is 23,500 times. Sulfur hexafluoride, 23,500 times than carbon dioxide. And once it is emitted into the Earth's atmosphere, it can stay there for 3,200 years. 3,200 years. Which means there are different type of greenhouse gases are there. Among the greenhouse gases, the most important greenhouse gas by volume is carbon dioxide. But based on the potential, it is not carbon dioxide. There are other gases which are having highly potential than carbon dioxide, which means sulfur hexafluoride is having a 23,500 times than carbon dioxide. That much of potential is there. Within that 100-year time, if this gas is staying in that atmosphere, it can produce this much of global warming tendencies. That is that. That is a one time, that is a carbon dioxide. Within 100, carbon dioxide is having a very limited capacity. Compared to carbon dioxide, within that 100-year times, these other gases can produce that much of heat energy. That's it. Next is a water vapor. Water vapor. What is water vapor? What is water vapor? Water in a gaseous form. Gaseous form, water in a gaseous form, which is the result of evaporation. So from the water surface, there will be evaporation will be taking place. And after the evaporation, most of this gases will get distributed within the air as water vapor. That is a gas. It's a part of the water cycle. Water cycle is having evaporation, condensation, precipitation processes. So evaporation means it's the conversion of liquid water into gas. Condensation is the conversion of gas into liquid. And when that liquid is heavier, that will fall down as rainfall or snowfall. So these are the different stages of the water cycle. So within this water cycle, water vapor is a stage. The distribution varies. The distribution varies from 0 to 0.02 percentage, from 0.02 percentage in the polar region to 4 percentage within the equatorial atmosphere. Ninety percentage of water vapor. 90% of water vapor. 90% of water vapor is present within 6 kilometers from the surface. Within 6 kilometers from the surface. 90% of water vapor is within 6 kilometers from the surface, which means Water vapor is maximum in quantity in the sea level or the low-lying areas of the atmosphere. When I climb in the Everest, when I climb into the upper atmospheric part, there the water vapor amount will get decreased or reduced rapidly. Fine. Water vapor can absorb water vapor can absorb both incoming solar radiation in bracket you can put near infrared radiation and outgoing terrestrial radiation. Water vapor is having greater greenhouse gas potential. Water vapor is having greater greenhouse gas potential. It's an important component. Of Earth's heat budget. It's an important component of Earth's heat budget or energy transfer. Which means I'll ask you one thing. When you stand in the Karol Bagh around 12 p.m. or around 2 p.m. in the noon, what will be the temperature in the month of April or May? You have not experienced. Already experienced. April. Okay, you have been here for? Oh my God, 4 years. All right. So how is the temperature in April? Around 40-50 degrees Celsius is there, right? So at Karol Bagh, you are experiencing around a temperature of around 45 degrees Celsius. How is that temperature? It's very hot, right? The same you are coming in the same location at around 5 a.m. the next day. What will be the temperature there? Five a.m. 28 will be the? No? It's around 20, 22, and that's possible. And sometimes it is less than that also. Which means I'm taking around 15 degrees Celsius, the cool time. Which means you're standing at Karol Bagh at around 12 or 2 p.m. at the noon. You have recorded a temperature of 45 degrees Celsius, and you are coming back to the same location in the next day early morning, that's the 5 a.m. You are recording a temperature of around 15 degrees Celsius. So, which means where all those heat energy went? Where was that? There was 45 degrees Celsius temperature. Right now at 5 a.m., it is just 15 degrees Celsius. What is that heat energy? What is that heat energy? It is absorbed by? What is that heat energy? Which means that after 5 a.m., 8 a.m. or 9 a.m. morning, you will start experiencing a spike in the temperature. From 15, it'll move up to 20 degree, 25. Likewise, the temperature will increase. And around the next day, 2 p.m., the temperature will be around 46 or 45. Again, in the next day, at around 5 a.m., you are visiting the same location, you will be recording a temperature of 15 degrees Celsius, which means there is a continuous exchange of heat energy is taking place between the planet's surface and the outer atmosphere. And within this exchange of heat energy, water vapor has a major role to play here. Fine. What is that role? Water vapor is one among the components that transfer heat from the surface of Earth towards the upper part of the atmosphere, which means this is the liquid. Suppose there is a lake. This is a water surface. From the water surface, continuously there will be evaporation will be taking place. Evaporation is a process. Evaporation is a process where you can expect conversion of liquid into gas. Liquid into gas. Which means from the lake, water will start converting into water vapor. Which means liquid to gas conversion that require absorption of heat energy. For this evaporation to take place from the water surface, this water body or water molecules require absorption of heat from the surroundings. So they will absorb heat from the surroundings. And that heat will be stored inside the water vapor as a hidden form. That is called as latent heat of vaporization. This is one among the reasons why that much of heat is lost from Karol Bagh around 5 a.m. in the next day. Some amount of water or some amount of heat is absorbed by the water surface to absorb or for the conversion of liquid water into water vapor. That process is called as evaporation. Evaporation, absorb heat from the surroundings, pack it inside the water vapor. Water vapor will move on to upper part of the troposphere. And there it will redistribute that heat energy. Slowly that heat will get radiated towards the space, which means they are like a courier agent. Water vapor is absorbing heat from the surface, releasing here. Absorbing from here, releasing here. So this is why water vapor is considered as an important component of Earth heat budget or energy transfer. Water vapor absorb heat energy. Water vapor absorb heat energy. Water vapor absorb heat energy. As latent heat of vapor, as latent heat of vapor, as latent heat of vapor, and it releases the heat, and it releases the heat, and it releases the heat. Into the upper part of troposphere, into the upper part of troposphere, into the upper part of troposphere as latent heat of condensation. As latent heat of condensation. What is condensation process? I'll give you an outline here. What is condensation process? Yes? Condensation means it's a conversion of water vapor or gas into liquid. Gas into liquid. Which means water vapor into water. Water vapor into water. That conversion require release of latent heat of energy, latent heat energy. So that conversion release heat energy. That conversion releases heat energy. Evaporation absorbs heat energy from the surroundings. Condensation releases heat energy into the air. Then only condensation will take place. Otherwise, there is no condensation. Evaporation is a conversion of liquid to gas, which require absorption of heat, latent heat of vapor. Condensation is a process of conversion of water vapor or gas into liquid, which require release of heat. So that is a latent heat of condensation. So from the surface of Earth, absorption. In the upper part of troposphere, release of heat, latent heat of condensation is released. The moisture holding capacity of air, the moisture holding capacity of air, the moisture holding capacity of the air is directly proportional to the temperature of the air. The moisture holding capacity of the air is directly proportional to the temperature of the air. Moisture holding capacity of the air is directly proportional to the temperature of the air. What is it? When the temperature of a column of air increases, its capacity to hold water vapor also increases. When the temperature of air increases, what happens there? Suppose this is a column of air. There is a lot of air molecules are there. When we apply heat energy into this column of air, what happens? What happens here? The space between the air molecules will increases, which means there is a thermal expansion will take place within the same column of air. The space between the air molecules will increase, thermal expansion will take place. This is called as a thermal expansion. When thermal expansion take place, more pore spaces will get opened within this column of air. More pore spaces will get opened, which can accommodate water vapor. Thermal expansion of a column of air causes opening of more pore spaces within this column of air, which can accommodate additional amount of water vapor. That's why I said the temperature of the air and the water holding capacity of the air is directly proportional. When the temperature increases, thermal expansion will take place, more pore spaces will get opened in the air column. As a result of that, more water vapor it can accommodate. If I'm withdrawing or making the heat energy from this column of air withdrawn, that is, I'm dropping the temperature. I'm cooling this column of air. If I'm cooling this column of air, what happens? The molecules will contract. The air molecules or the expanded air will contract. When that contraction takes place, all those opened pore spaces will start contracting. They will close. When that pore spaces are closed, there won't be much place for water vapor to get accommodated. So this is how temperature and water holding capacity of a column of air is related. When the temperature increases, water holding capacity of the column of air increases. When the temperature drops down, water holding capacity of the air drops down. And that is directly related with the thermal expansion and contraction. Fine. What are the three different units to measure water vapor content in the air? Relative humidity, absolute humidity, specific humidity. Fine. So three different units to measure water vapor content is absolute humidity, specific humidity, relative humidity. Absolute humidity, relative humidity, and specific humidity. Next is dust particles. Dust particles. Dust particles, or can also be called as an aerosols. Dust particles or aerosols. What are the sources of dust particles? What are the sources of dust particles? What are the different sources of dust particles in the air? Volcanic eruption. The materials lifted by winds. Then dust particles. One is obviously volcanic eruption. Second one is meteorite. Meteorite. The burned remains of meteorites. So the sources are volcanic dust, meteor dust, sea salt, volcanic dust, meteor dust, sea salt, smoke and soot, salt, S-A-L-T, soot, S-O-O-T. What is a soot? It's a substance that you can find in the chimneys. Chimneys, yeah. The fine grained black, a shiny black material is there in the chimneys. That's the soot. The smoke and soot is another source. Pollen and various organisms lifted by winds. Pollen grains of any plants, pollens and various organisms lifted by winds is another source of dust particles. Dust particle which is present in the Earth's atmosphere causes. Dust particles which is present in the Earth's atmosphere causes reflection, selective scattering, reflection, selective scattering, and absorption of incoming solar radiation. And absorption of incoming solar radiation. Absorption of incoming solar radiation. The selective scattering process, the selective scattering process gives different hues in the sky, different hues or colors in the sky. That is selective scattering. Sometimes the sky appears blue, sometimes it is red, orange. All those colors are a result of selective scattering caused by aerosols or dust particles. Fine. Dust particles, especially sea salt, are hygroscopic nucleus. Are hygroscopic nucleus. What are hygroscopic nucleus? Hygroscopic nucleus are something that has a capacity to attract water molecules. water attractive substance. They are actually the foundation or building blocks of clouds. So hygroscopic nuclei, which are scattered in the sky, are capable of attracting water molecules towards them, and they can provide a platform for the building clouds. So this is how the clouds are created. The huge clouds will be created like this. Dust particles which are scattered here and there can attract water molecules, and they can build huge sized clouds like this. They are the raw material for the cloud formation, especially within the tropics. The concentration of dust particles are maximum at the subtropical regions. And the amount of dust particle is very less. In the equatorial atmosphere. The concentration of dust particle is very less in the equatorial atmosphere because of that's what I'm asking. That's a question. Don't wait for the word for me. What is the reason? Yeah. Rainfall because of 4 o'clock showers. Equatorial region has a regular rainfall, which means 365 days there is continuous rainfall at around evening, around 4 o'clock. So regular rainfall is capable of flushing out all the available dust content within the equatorial atmosphere. So that's why equatorial sky is having a less presence of dust compared to subtropics. Subtropics are regions of no rainfall. Equatorial regions are a region known for rainfall throughout the year. So this is the dust particles. Next is Earth's atmosphere, structure of Earth's atmosphere. Structure of Earth's atmosphere. Fine. So have you went through the pre-YQs of geography? Previous year question papers. So how many questions have been asked for the past 10 years? If you take the count of geography questions from 2015 up to 2024, 150 questions were asked from geography, which include conventional as well as map-based questions. So 10 years, 150 questions. And from the conventional area, for the last 10 years, 52 questions were from the conventional areas and 98 questions were from maps. That is a map of India and the world. As far as this conventional area is concerned, out of this 52, 17 questions were asked from climatology and world climatic regions. There are 3 questions were from geomorphology. There were around 7 questions from oceanography. 17 questions were from climatology, which means there is a high potential for asking questions from climatology part. Here, everything is conceptual based things. So you need to have an understanding, thorough understanding regarding the concept of all these topics. So clarify all your doubts if there is any doubt while the discussion goes on, and we'll clarify it. All right. So any doubts till here? We have been discussing about climate and weather. Then we discuss about evolution of Earth's atmosphere. Then we discuss about composition of Earth's atmosphere. It is done. Next part is the structure of Earth's atmosphere. There we need to discuss about the composition based layering of Earth's atmosphere. Then structure of Earth's atmosphere based on vertical distribution of temperature. That's the troposphere, stratosphere, mesosphere things. That is the area of discussion in the next session after the break. Any doubts, please? No. Yeah, please. Yeah. Latent heat part, anyways, we'll be covering it in the condensed water cycle, which means evaporation, condensation, precipitation, that will cover. Anyway, since there is a doubt, I'll clarify after the break. What is the doubt exactly? Latent heat means the heat, latent heat of vaporization means the heat required for a volume of liquid to get converted into gas, which means I have 10 ml of water. For this 10 milliliter of water, if I need to convert it into gas, that is a water vapor, it requires an amount of heat energy. It requires that heat energy. It need to be, it is a requirement. Otherwise, there is no possibility for that conversion. So that required heat for converting this much of liquid into gas is called as latent heat of vaporization. All right. And that much of amount of heat will be stored inside this water vapor as a hidden energy. Fine. So liquid got converted into gas. That much of heat is stored inside this water vapor. And this water vapor will hold that heat and it will move on to the upper part of the troposphere where it starts the cooling process. Condensation is the next stage. Condensation means conversion of gas into liquid, just the opposite thing of evaporation. So what is the requirement? What does water vapor need to do? It need to release that heat. Then only there is a possibility for condensation process from gas to liquid. Oh, fine. So that is the requirement of a heat energy for phase transfer. When it is a liquid to gas transfer, it needs absorption. When it is a gas to liquid transfer, it needs release. That's it. Yeah. Any other doubts? No? We'll go for the break, and after that, we'll start the discussion with the structure. Welcome back to the next session. Structure of Earth's atmosphere. Online, don't go. Today's break will be at 2:30. Structure of Earth's atmosphere. Structure of Earth's atmosphere. Here, the topic of discussion is, right now we have discussed about the composition. There are different types of gases, water vapor, dust particles, their importance, their significance, everything is discussed. Next is atmosphere layering. That is the structure of the atmosphere. That is the topic. We can approach this topic basically in two different ways. One is based on the structuring of Earth's atmosphere can be done based on the composition. Composition based structuring, we can do that. Second one is based on the vertical distribution of temperature. So these are the two different method of stratification of the atmosphere. There is one more, that is a density based. But that is not having much significance or importance. This is the two major areas. So the Earth's atmospheric structure of Earth's atmosphere. Or layering of Earth's atmosphere. So based on the composition of gases which is present in the Earth's atmosphere, we can classify the entire atmosphere of Earth into two important parts. One is homosphere. Second one is heterosphere. So these are the two layers based on the composition of gases. Homosphere, heterosphere. Homosphere lasts up to 88 kilometers. From the Earth's surface up to 88 kilometers, it is called as a homosphere. And beyond 88 kilometers, 88 kilometer plus, that is called as a heterosphere. Beyond 88 kilometer, that is called as a heterosphere. First one is a homosphere. Extends from Earth's surface up to 88 kilometers. Even though atmosphere rapidly decreases in density with increase in altitude. With increase in altitude, the composition of gases remains the same up to 88 kilometers. And the composition is like this: nitrogen 78, oxygen 21, argon 0.03, carbon dioxide argon 0.93, CO2 0.03. This percentage will remain the same up to 88 kilometers. This part is called as homosphere. This 88 is not a watertight valley. It will vary. Sometimes it will be 80, sometimes 82. It'll have a range. The exception in the homosphere, are the concentration of are the concentration of, what are the exceptions? Tell me. Up to 88 kilometers, there is a uniform pattern as I mentioned, 78 nitrogen, 21 oxygen, 0.93 argon, 0.03 carbon dioxide. But there are two exceptions. What are those exceptions? Two exceptions are there. One is at a height of around 20 to 35 kilometers or 25 to 35 kilometers. Second one is the lower part of the Earth's atmosphere at the equatorial regions and subtropics. What is that? What are those exceptions? One is the presence of ozone. Two exceptions. Exceptions in the homosphere are the concentration of O3, ozone, in the stratosphere in the stratosphere, 25 to 50 kilometers. And varied distribution of water vapor and dust particles, in the lower atmosphere. So what does it mean? At around 25 to 50 kilometers in the stratosphere, there we have a major concentration of ozone. There, this composition will have a slight variation. That is one exception. Second exception is, within the lower part of the atmosphere, there are certain regions which are known for rich water vapor content. There are certain regions that are known for very dry conditions. Very similar to that, there are regions known for high concentration of dust particles and less concentration of dust. As I mentioned, within the equatorial atmosphere, dust content is less, subtropics dust is more. Which means when these three components comes together, there will be some compositional difference regionally. So that is what making the homosphere some exceptions. This uniform composition was attained. Around 600 million years ago. Next is heterosphere. Heterosphere appears beyond 88 kilometers. Beyond 88 kilometers. Appears beyond 88 kilometers. The gases in this layer are not evenly mixed. The gases in this layer are not evenly mixed. Evenly mixed. Not evenly mixed. Here the air is highly rarefied. Here the air is highly rarefied. Air is highly rarefied. Which means, do you remember, around 90% of the Earth's gases, atmospheric gases, is concentrated within 29 kilometers. Which means most of the concentration of gases are there in the lower part. As you climb 50 kilometers, 60, 70, 80, likewise, if you are moving upward, the air column molecules are very, very rarefied. Their concentration is maximum at the surface area and it decreases upwards. Fine. So because of this, within the heterosphere, which appears beyond 88 kilometers, that concentration of gases is very, very limited. So however, for all the scientific purposes, for all the scientific purposes, the upper limit of the atmosphere is taken as 480 kilometers. 480 kilometers. Which means within the heterosphere, the gases are not like mixed as you can see it in the troposphere and stratosphere. There, each and every gases will appear as a separate layer, which means in this heterosphere, the lower part you have the nitrogen layer. So you can write 88 to 100 or 105. It is the nitrogen layer. One not 5 to 125. Oxygen. (125 to 150). Helium. 150 plus hydrogen. 150 plus hydrogen. So this is how the gases are layered within the lower part of the heterosphere. So first one is a nitrogen, oxygen, helium and hydrogen. This is how they are layered. And below that, which is a part of the homosphere, where you can expect a perfect mixing of these gases. They act like a single gas. But beyond that, there is a gases are highly rarefied and there is a gases are segregated according to their molecular weight. So segregation will be there. Next is the most important part, division of atmosphere based on the vertical distribution of temperature. Vertical distribution of atmosphere based on the vertical distribution of temperature. What is the source of heating for the Earth's atmosphere? Insolation, right? Source of heating for the Earth's atmosphere is insolation. Incoming solar radiation is the source of heat energy. Fine. So the source of heat energy is insolation, which stands for incoming shortwave solar radiation. But when you stand at the lower part, the low-lying area, you experience a temperature of around, suppose, a 40-50 degrees Celsius. When you climb a mountain like Himalayas, you will experience a continuous drop in the temperature condition. Some temperature reaches -5 degrees Celsius, -20 degrees Celsius and all. But here the picture is, you are moving close to the source of energy, which means this is the place you are standing. This is the mountain you are going to climb. This is the source of heat energy. Source of heat is incoming solar radiation. You are moving close to the source of heat, which means when while you are standing at the Indo-Gangetic plain, or you are standing at Delhi, you are at a depth at a height of around 100 to 200 meters from mean sea level. From there, you are climbing the Everest. By climbing the Everest, you are moving close to the sun, around 9 kilometers closer. But still you experience a drop in the temperature. From Everest, you are coming down to Delhi. You are moving away from the sun. 9 kilometers away from the sun, you experience an increase in the temperature. Why so? Terrestrial radiation. What is their role? Is that the source of heating? Source of heat energy is sun, right? But when you're moving close to the sun, you are experiencing a drop in the temperature. When you are coming down to Delhi, you are experiencing an increase in the temperature. In fact, you are around 9 kilometers moving away from the sun. Still, you are experiencing a spike in the temperature. Why? Why hill stations record a low temperature than the plains? That is the question. Is it because of the pollution? I'm taking you into Amazon rainforest. No pollution there. Or any other places where there is no pollution. Even though you are there, you can experience the same. So it's not the pollution, something else. What is that? Troposphere. We are in the troposphere. Fine. Heated by? That's the point. Terrestrial radiation. Fine. That's the point. So heated by the terrestrial radiation. So heated by the terrestrial radiation means outgoing terrestrial radiation. It is a radiation starting from Earth's surface, right? When I'm standing here at Delhi, I'm standing at the Earth's surface. That is a source of terrestrial radiation. When I'm standing at Everest, there also I'm standing at Everest, right? That is also a source of terrestrial radiation. Then what is the difference? There comes the difference that you have mentioned. What is it? Not pollution exactly, but something different. Something associated with the composition. Yeah. What is, who is responsible for that? It's not water. It is not dust particles. Water vapor is one among that. And what is their common group name? Among the gases, they have a common group. What is that? Huh? No. Greenhouse gases. That is the culprit. Fine. So, so the structure of the Earth's atmosphere based on the vertical distribution of temperature is almost like this. You can see that. This is the Earth's surface. This is the altitude. And this is the temperature line. altitude and temperature line. Say for example, this is 0 degree. This is 10, 20, 30, 40, 50, 60. Likewise, the temperature will go so on. And this is the altitude. This is -10, -20, -30, -40, -50, 60, 70, 80, 90. Likewise, it will go. It goes on like this. 120, 130, all these are mentioned. Or from here, I'll change the values. 50, 75, 100, 125, minus. So when I observe the temperature distribution, vertical temperature distribution, and the planet atmosphere all together, here we don't have troposphere, stratosphere, mesosphere, nothing else here. Just we are observing the temperature condition. When I observe the temperature at the surface of Earth, it is recorded around 40 degrees Celsius. And when I climb 1 kilometer, 2 kilometer, 3 kilometer, likewise, what I am observing is there is a continuous drop in the temperature. There is a continuous drop in the temperature. 20, 40, 60, 80, 100, likewise, that goes. Then there is a continuous spike in the temperature. Then there is a continuous drop in the temperature. It's a continuous drop in the temperature. So this is the pattern of distribution of temperature. So what I have observed is this is the pattern of the temperature distribution of Earth's atmosphere. The distribution of vertical distribution of solar radiation or the vertical distribution of temperature in the Earth's atmosphere is not uniform. When I climb from the surface of Earth into 10 kilometer, 20 kilometer, 30 kilometer, I can experience there is a varied distribution of temperature. The temperature distribution is not uniform throughout the entire length and breadth of the Earth's atmosphere. And the first few kilometers, what I am observing is there is a continuous drop in the temperature. And that drop of temperature lasts almost up to 18 kilometers at the equator. And after that, slowly, I can sense there is a change in the pattern of the temperature distribution. Temperature distribution, that is a drop of temperature, ceases after 18 kilometers. And there is an isothermal condition exists for a few kilometers. Then you can see that there is a temperature increase with increase in height. Again, this increase of temperature lasts up to 50 kilometers. Beyond that 50 kilometers, you can find there is an isothermal condition is there, which means there is no much changes in the temperature. Again, the temperature drops and records the maximum possible minimum temperature, possible temperature in the Earth's atmosphere. After that, temperature increases exponentially. So this is how the vertical distribution of temperature can be observed in the Earth's atmosphere. And based on this pattern of temperature distribution, vertical temperature distribution, we have divided the Earth's atmosphere into different layers. The first few kilometers where we can experience continuous drop of temperature. Till that place or that height where the temperature drops continuously, that layer is called as troposphere. This layer is called as troposphere. Beyond that, there is a layer with an increase of temperature with increase in altitude, which is just opposite of the troposphere. That is called as stratosphere. Next, there is a continuous drop of temperature with increase in height, and that layer is called as mesosphere. And beyond 80 kilometers, there the temperature again increases with increase in height. That is called as thermosphere. So these are the vertical layers of Earth's atmosphere. And this layering is based on the vertical distribution of temperature. Variation in the vertical distribution of temperature made this much of layers possible. Troposphere, stratosphere, mesosphere, thermosphere, likewise the layers are there. And within the thermosphere, there is this area which is called as an ionosphere is also there. And this layering is not based on the composition. This layer is based on the vertical distribution of temperature. Earlier distribution, that is a composition based distribution, homosphere and heterosphere was there. This one is based on the vertical distribution of temperature. Fine. Any doubts? Which is the lowest atmospheric layer? Troposphere. Fine. Which atmospheric layer is called as a weather layer? Troposphere. Which atmospheric layer is known for ozone layer? Stratosphere. Which atmosphere is known for large concentration of charged particles? Yes, within the thermosphere, ionospheric part. Fine. Which atmospheric layer or its attribute is used for navigation and radio transmission? Ionosphere. Where you have maximum concentration of ions that will have a capacity to reflect radio waves. That is used for radio broadcasting in early times. Fine. Which atmospheric layer where we have convection possible? Convection possible only in one layer. That layer is also called as a layer of mixing. These are the points that we are going to discuss after the break. So I'm just giving you a brief idea. So what is it? There is nothing. There is nothing. Yeah, here. Yeah. A layer of mixing, a layer of convection. All these are attributes of troposphere. Troposphere is the atmospheric layer where you can find air is convecting. What are the advantages of, what is the convection of air? Movement, the vertical movement of air column. What for this air column is moving vertically? Because of for heating the upper part of the air column. That is the reason. So convection is a mechanism to transfer heat energy. That's all. So next area of our discussion will be the layers of atmosphere. So we'll start with the troposphere. All right. So next session after the break will start around 3 o'clock. Yes. So, can you hear me? The next area of discussion is the layers of atmosphere. So, as I mentioned, there are two classification, the layers according to the structure of the atmosphere. One classification is based on the composition, that is a homosphere and heterosphere. Second classification is, that is the most important classification, it is based on the vertical distribution of temperature. And based on the vertical distribution of temperature, this is how the pattern of distribution of temperature. Vertically, you can see that in the first few kilometers, say for example, 18 kilometers at the equator, 13 kilometers at the middle latitude, and 6 kilometers in the polar region. The first few kilometers, the temperature is having a tendency of a drop of temperature like this. So temperature decreases with increase in height. And after reaching a height of around 18 kilometers at the equator, that drop of temperature will cease, which means that will stop. Drop won't be there anymore. And there you can see that there is a stagnation in the temperature pattern or changes in the temperature. There is no change, visible change is not taking place here. What is continuing, it is stopped over here. And after that, you can see that there is a isothermal condition, which means there is no increase or there is no decrease. What was the range of temperature is attained at 18 kilometers? It continues for around 5 kilometers in the lower stratosphere. That is what we can call it as an isothermal condition. And after that, 25 kilometers onwards, you can find there is an increase of temperature with increase in height. And that increase of temperature with increase in altitude ranges up to 50 kilometers. And beyond 50 kilometers, that increase of temperature also ceases. Then it attains a status quo kind of thing like this here. Then again, gradually you can find the temperature decreases with increase in height. And that decrease of temperature with increase in height lasts up to 88 kilometers. And beyond that, you can find there is a rapid increase of temperature with increase in height. So this vertical pattern of temperature distribution, based on this vertical pattern of temperature distribution, the entire atmosphere is layered into different stratas that we can call it as a layers. So the first layer is called as a troposphere, second is stratosphere, mesosphere, and thermosphere. So let's see the first one, that is a troposphere. First layer of Earth's atmosphere. Troposphere. Troposphere. So here the pattern of temperature distribution is like this. 0, 5, 10, 15, 20, 25, 30, 35. Likewise, the temperature will go. From here, I'm starting the temperature as a surface temperature. Temperature decreases with increase in height. And here it is around minus 80 degrees Celsius. It reaches up to here. So the temperature decreases with increase in height. And after that, it attained the height, the maximum limit of tropospheric temperature, minimum limit of tropospheric temperature. And after that, you can find there is an isothermal condition. So this is the pattern of temperature distribution in the troposphere, where the temperature decreases with increase in height. Temperature decreases with increase in height. Troposphere is the lowermost layer of atmosphere. the lowermost layer of atmosphere. Have you seen the PYQ this year, 2024 prelims, regarding the troposphere and its varying height? So write it. Lowermost atmospheric layer ranges up to 18 kilometers at the equator. 18 kilometers at the equator. (13 kilometers at the mid-latitude). 13 kilometers at the mid-latitude. (6 kilometers the polar region). 6 kilometers at the polar region. And in 2024, this, don't write. 2024, the question was like this. Troposphere attained its maximum height at the equator. That was the first statement. And there was a reason also mentioned. That was the second statement. So as I mentioned, troposphere attained 13 kilometers at the middle latitude, 18 kilometers at the equator, 6 kilometers in the polar region. What is the reason for this varying height of troposphere? It is closest to the Earth's surface. Fine. Is that the reason? No. Inclination of sun rays can also be experienced in stratosphere, mesosphere, thermosphere. All the layers you can experience the inclination. No. And that was the second statement in that question. That maximum height of equator is caused by what cell? No. Convectional cells. So the maximum height of equator, maximum height of troposphere at the equator is because of the high rate of air convection. So troposphere is the lowermost atmospheric layer, attain maximum height at the equator 18, 13 at the mid latitude, 6 at the polar region. This maximum height of equator, maximum height at the equator is caused by, maximum height at the equator is caused by the convectional heat transfer. The convectional heat transfer. Which means, in a very simplistic understanding, it is like this. Say, for example, I have a balloon. I have a balloon at my hand, and I am pumping maximum amount of air into this column of balloon. I am pumping maximum air into the balloon so that you can see that the balloon will expand like this. This is how the balloon will expand. As much as air is pumped into the balloon, it can expand like this. The troposphere is also like this, where that pumping mechanism is done by the convections. Wherever we have a high rate of air convection, there the troposphere can expand maximum. Wherever the convection rates are less, there the troposphere attain at a minimum levels. Which means here the pumping mechanism is done by convections, air heat convection. Heat convection means convection is a mechanism of vertical heat transfer. Wherever we have maximum convection, there you can expect maximum height of troposphere. Wherever we have a minimum convection, there the height of troposphere will be minimum. So Convection will be maximum in those regions where you have high amount of incoming solar radiation. High amount of heat, that region has the potential to generate maximum level of convection. So when there is a maximum level of convection is produced, it can make the troposphere at maximum height. So this is ultimately decided by the insolation. Insolation. Insolation decides the temperature condition of a place. That temperature decides the convection cells. Yeah. I'll give you one more diagram. Hello, hello. Hello, hello. Fine. What happened? Okay, fine, fine. Okay, fine. Can I continue? Fine, fine. Yes. So when I move away from the equator towards the polar regions of north or polar regions of south, the amount of incoming solar radiation or its intensity will be affected, which means within the tropics, tropic is the regions, within the tropic is the region that receive maximum amount of insolation. So when a place receives high amount of insolation, that place will have a capacity, maximum capacity to generate high rate of air convection. So within the tropics, especially the equatorial regions, you can expect high rate of air convection cells like this. Convection will be starting from here like this. Whereas in the mid latitude, I have a limited amount of insolation where I can expect only this much of convection. Within the polar region, I have a very limited amount of insolation, so that generates very less amount of convection. And according to this convection, that height of the troposphere varies like this. Yeah, it's maximum at the equatorial areas. So this was the statement question asked in 2024 prelims. The height of troposphere is maximum at the equator, and this maximum height of troposphere at the equator is caused by high rate of air convection. Troposphere contain 90% of the total mass of atmosphere. Troposphere contain 90% of the total mass of atmosphere. %90 of the total mass of Earth's atmosphere. The entire weather phenomenon is associated with troposphere, is associated with troposphere, is associated with troposphere. So it is also called as a weather layer. It is also called as a weather layer. Why all the weather phenomena are associated with troposphere only? Because of? No. All the weather phenomena are associated with troposphere. That's why it is also called as a weather layer. Why all the weather phenomena are restricted with the troposphere? Because this is the atmospheric layer where you have the abundant water vapor and the dust particles. This is the atmospheric layer where you have all the water vapor, dust particles and clouds. An important aspect of troposphere is the next point. Within the troposphere, there is a continuous drop of temperature with increase in height. The temperature profile is like this. Within the troposphere, there is a continuous drop of temperature. Temperature decreases with increase in altitude. Temperature decreases with increase in altitude. What is the reason for that? What is the reason for that? I'll give you some more idea regarding this. Temperature drops with an increase in altitude. And this drop of temperature with increase in altitude is called as lapse rate. The drop of temperature with increase in altitude is called as a lapse rate. The drop of temperature with increase in altitude. One second. Just strike it out, strike it out. There is a conceptual mistake in that statement. Temperature drops with an increase in altitude at varying rates at various places. At varying rates at various places. At varying rates at various places. On an average, it is 6.5 degrees Celsius per kilometer. On an average, it is 6.5 degrees Celsius per kilometer, which is called as normal lapse rate. Or it is also called as environmental lapse rate. Normal lapse rate or environmental lapse rate. Whereas a lapse rate is highly varying, which means that varies from place to place, that varies from season to season, that varies between day and night. Within a single place itself, you can find different lapse rate at different seasons between day and night. So an average value is taken as 6.5 degrees Celsius drop of temperature with increase with 1 kilometer. That is environmental lapse rate or normal lapse rate. So keep in mind, drop of temperature with increase in altitude, the phenomenon is not called as lapse rate. Lapse rate is only a rate at which the temperature decreases. So lapse rate itself says I am a rate. lapse rate. It's not the name of the phenomenon, or it is not the cause behind this phenomenon. So it's just a rate of change. And what is the cause of this drop of temperature? What is it? You know the cause. What is it? Yeah. Greenhouse gas. Then anything else? Let's see this. When I'm here, I record a temperature of, when I'm standing at the surface, of Earth, I record a temperature of around, what is the temperature? 40 degrees Celsius. When I climb the air, the free air, like this, I can record a temperature of around a drop of temperature, continuous drop of temperature. At a kilometer of around 18 kilometers, I can even record a temperature of minus 60 degrees Celsius or minus 90 degrees Celsius. This drop of temperature is caused by an important factor. You can see this. So, one is the troposphere is heated by the terrestrial radiation. Troposphere is heated by the terrestrial radiation, which means Earth's surface is the source of heating for troposphere. The lowermost atmospheric layer is not heated by the direct solar radiation. It is heated by the outgoing terrestrial radiation. So that is a source, which means when I am standing at the surface of Earth, I am standing at the source of heating. And when I am moving away from the surface like this, I am moving away from the source of heat, which means gradually I can see that there is a drop of temperature. So this is why there is a drop of temperature within the free air within the troposphere. Got it? So for me, this is, I'm standing here, and this is the 1 kilometer, 2 kilometer, 3 kilometer, 4 kilometer, 5 kilometer. This is how the troposphere counts, which means gradually I'm moving close to the sun. But within the troposphere, the phenomenon is, I can sense there is a continuous drop of temperature with increase in height, which means at the surface, I can experience 40 degrees Celsius temperature. At around 10 or 15 kilometers, I can sense there is a temperature difference of around minus 60 or minus 90 I can record. So around in the upper part of the troposphere, the equatorial region, temperature is around minus 90 or minus 80 degrees Celsius is very common. Even though I'm moving close to the sun, I'm recording a drop of temperature, that too less than 0. Fine. How is it possible? The answer is, for the troposphere, that is the first primary atmospheric layer or lower and lowest atmospheric layer, it is not the incoming solar radiation is not the source of heating. The reason is, incoming solar radiation is coming as a short wave solar radiation. They are short wavelength format. And the particles that are present in the troposphere is incapable of absorbing this short wave solar radiation and heat by themselves. It is incapable. Some amount is absorbed by water vapor, but it is not creating a huge impact. So they are incapable of absorbing this incoming solar radiation. So for incoming solar radiation, troposphere is largely transparent. They can easily pass through the troposphere and hit the surface of Earth, and they heat up the surface first. Earth's surface, the roads, the rocks, the soil, the vegetation, the buildings, everything will be heated first. And after that, the Earth's surface start a counter radiation from the Earth's surface. This counter radiation is called as outgoing terrestrial radiation, or it is also called as outgoing Earth radiation. This outgoing Earth radiation is in long wave format, not short wave as incoming solar radiation is coming. They are long wave. And this long wave radiation, when it is emitted from the Earth's surface, when it is passing through the troposphere, there the particles like greenhouse gases, water vapor, all these particles can easily absorb and block this terrestrial radiation because right now they are in long wave format. Their wavelength and the size of the particle is right now matching. They can block it, they can heat up the troposphere right now. That's why this heating agent of troposphere is not the incoming short wave solar radiation, but it is the outgoing long wave terrestrial radiation. That's the point. Then so this concept is having a bit difference from the other concept. What is it? Here within the troposphere, 6.5 degrees Celsius difference is there. Here within a hill station, there is a difference is there. In the hill station, what is the additional thing? When I'm standing at the hill station, I'm standing at the surface of Earth. There also I'm standing at the Earth surface. Here also I'm standing at the Earth surface. Both this hill station and this surface also receives shortwave incoming solar radiation. From here and from here also, long wave terrestrial radiation will start. All right. So here we are comparing a plain area and a hill station. In both the condition, I'm standing at the surface of Earth. Both this location, surface, experience the incoming solar radiation. Take an example of Delhi and Himalayas or Everest. Everest is a surface of Earth. That is also a source of terrestrial radiation. Delhi is also on the surface. That is also a source of terrestrial radiation. When I'm standing at the Himalayas or when I'm standing at Delhi, in both the cases, I'm standing at the source of heating, source of terrestrial radiation. Even though I'm standing at the source of terrestrial radiation at Himalayas or Everest, I'm not able to record a high temperature there. Temperature is in minus degrees. Even though both the locations are capable of receiving incoming solar radiation, both the locations are capable of releasing terrestrial radiation, long wave terrestrial radiation. When I'm standing at a hill station, I can record minus degrees. When I'm standing at a plain, I can record 40 or 50 degrees Celsius. Here the reason is, exact reason is the concentration of greenhouse gases. Both the locations release terrestrial radiation, but it is not just the release of terrestrial. Everest is also releasing terrestrial radiation, but there comes an importance, the blanket effect. That greenhouse gas is a typical feature. What is the significance? Greenhouse gas will act like a blanket. Just like a blanket. What is the purpose of using a blanket or jacket during winters? To to protect us from cold condition. How is this blanket is protecting us? By trapping heat which is radiating heat. When there is a thick layers of greenhouse gases present in a place, they will act like a thick blanket. They will block the releasing heat energy and they will recirculate that heat in the same location. So that heat will be preserved over there. This is what happens in Delhi. Whereas in Himalayas or any other hill station, this greenhouse gas is very, very thin. Carbon dioxide, water vapor, everything is in very, very less concentration. So within a hill station, what is the condition is, this one greenhouse gas concentration is only like this. From there, terrestrial radiation will start. When the terrestrial radiation starts like this is exactly like when I'm using a very thin cotton blanket in Himalayas. When I use a very thin cotton blanket, what happens? Whatever heat is releasing from my body can easily escape by passing through this cotton blanket. Fine. Which means in Himalayas or any hill station, greenhouse gas concentration is very limited. Their blanket effect is very less. So whatever terrestrial radiation is starting from there can easily escape that atmosphere. So that is the reason behind the hill stations and plains are having a varying temperature condition. Got it? Should I run a bit faster? No? Yes? No? Yes or no? Yes. Yeah. Is it done? This is the only atmospheric layer. Troposphere is the only atmospheric layer. Troposphere is the only atmospheric layer which is known for air convection. Troposphere is the only atmospheric layer which is known for air convection. So it is also called as a convective layer. It's also called as a convective layer. Convective layer. So what is the convection? It's a mechanism of transferring heat from the terrestrial surface. The Earth's surface will be radiated into the lower part of the Earth atmosphere. So there is a process is called as a terrestrial radiation. That is a process. Through terrestrial radiation, Earth's surface release that heat. And the Earth's surface and the adjacent column of air will get or receive that heat energy through conduction. That is a process. Conduction. The lower atmosphere receive that heat through conduction. Conduction means Passage of heat through physical contact, which means if there is an iron box is kept on the table, switched on, when I touch that iron box, I can see that, I can sense that heat. That is because of the physical contact was attained. This is through conduction. So through conduction, the lower part of the Earth's atmosphere will receive the heat energy. And when this lower part is getting heated, that column of air is having a high amount of heat energy, that heat will be transferred into the upper part of the atmosphere through molecular movement. Air molecule will absorb that heat, transfer that heat into the upper part, which means the air molecule itself is in motion. It is not just the heat is transferred, it is the molecule is also in motion. That is what we can call it as a convection. The same mechanism that is taking place in the asthenosphere. From the site of radioactive disintegration, convective cells will be generated, magma will be running like this. Very similar to that, here the air will absorb the heat from here and that air will take that heat energy into the upper part. Like this is how that convection is working. Fine. So this is the convection. The troposphere is the only atmospheric layer where you can expect the convection. Because of the convection, there is a mixing of air is active in the troposphere. A layer of mixing. Troposphere is called as a layer of mixing. A mixing is continuous. Why there is a convection is active here? Why it is not there in stratosphere? For convection to take place, what I need is there is a thermal gradient is required, which means for convection to work on, I need a maximum concentration of heat at the surface. And there the temperature has to decrease continuously. This vertical distribution of heat energy is a precondition for convection to work on. If there is no differences in the temperature distribution between the low-lying areas of the troposphere and upper part of troposphere, there is no possibility for convection. And there is no requirement of convection. If the condition is there is no difference in the temperature. But within the troposphere, as we mentioned, lower part we have a high temperature, and as we are moving up in the troposphere, the temperature decreases. And that drop of temperature, heat energy, is the reason behind the convection to work on. Convection will take heat from here, pass on that heat into the upper part. Air molecules will become cooler. Again, it will come back. Again, it will take heat from here. It will move like this. This is how the convection works. So convection is working to equalize the distribution of temperature. And it is only possible in the tropospheric part. Upper boundary of troposphere. Upper boundary of troposphere is called as a tropopause. Upper boundary of troposphere is called as a tropopause. This is the place where This is the place where the drop of temperature ceases. The drop of temperature ceases. This is the place where a drop of temperature ceases. And a constant temperature prevails. I'll ask you one question based on the troposphere. This is the varying height of troposphere between the polar regions and the equator, tropical areas. Varying height. Maximum here, minimum in the polar region. Within this polar surface, Arctic or Antarctic region, the temperature is around 0 degrees Celsius. Within the tropical area, say for example, in Africa, Saharan desert, the surface temperature is around 50 degrees Celsius. We are moving vertically up in the tropopause. Towards the tropopause, we are moving from the surface up to the tropopause. Which tropopause will have the capacity to record the lowermost temperature? Is it the African tropopause or Antarctic or Arctic tropopause? This is the temperature at Antarctica surface. This is the Saharan temperature. In both the condition, I am taking you to the tropopause. In Antarctica, 0 degrees Celsius at the surface. Sahara, 50 degrees Celsius at the surface. Both this location, we are moving into the tropopause. In which tropopause you can record? You may possibly record the lowermost temperature. Think. We are moving from the frozen lands of Antarctica, and the next time we are taking off from the hot Saharan desert of 50 degrees Celsius. Saharan tropopause has the capacity to record the lowermost temperature in the tropopause. Yes? Antarctic. Sahara. Why Saharan? Majority of you are mentioning Saharan. No? Sorry. Which one? Antarctic. Why Antarctic? No, Antarctica is in 0 degrees. Yeah. The answer is Saharan tropopause. Why? The reason is when you are taking off from Sahara, at the surface you recorded 50 degrees Celsius. And you are moving away from the surface of 50 degrees Celsius. You are moving around 18 kilometers. Let's consider it as 20 kilometers. You are 20 kilometers away from Saharan surface. 20 kilometers means, if you are considering normal lapse rate, 6.5 into 20. What is that? Around 130 degrees Celsius difference of temperature will be there between surface of Sahara and upper part of tropopause of Sahara, which means 50 minus 130. What is it? Minus 70 or 80? Minus 80 degrees Celsius will be the temperature at the Saharan tropopause. Here you have 6 kilometers of height, right? 6 into 6.5. What is it? Around 39, or just take it as a 40, which means there is a 40 degrees Celsius difference will be there. You have a difference from 0 to 40. That means here you have minus 40 degrees Celsius. But here you have minus 80 degrees Celsius. This is possible because the varying height of the tropopause. Two reasons are there. One is the varying height of the tropopause. Maximum height, maximum lapse rate. 20 into 6.5. Next reason is, in the Arctic and Antarctic region, the surface is ice covered. Ice covered surface has a phenomenon called as a temperature inversion. Ice covered surface has a phenomenon called as a temperature inversion, which means most of the insulation that is striking on the surface will get reflected back. And if you are moving from frozen minus degree surface, there slowly you can sense there is an increase of temperature. Fine. We are moving away from the ice covered surface, moving away from the ice covered surface. Slowly you can sense there is a temperature spike, slight increase in the temperature, which means the drop of temperature in the polar region is not as you expect, which is experienced in the other parts. So there is a temperature inversion phenomenon is also present. Temperature inversion. When you move away from ice, polar ice, temperature increases slightly. So this condition exists in the polar region. So considering altogether within the tropopause of Sahara, within the tropopause of Antarctica or Arctic, the lowest minimum temperature you can experience is Saharan tropopause. Normal lapse rate. What I have here is a 50 degrees Celsius. Here I have as a 0 degrees Celsius. Within the troposphere, we are talking about the tropopause. Within the troposphere, there is a continuous drop of temperature with increase in height. As I'm moving 1 kilometer, 2 kilometer, 3 kilometer, there will be around 6.5 degrees Celsius per kilometer based deduction will be there in the temperature, which means when I'm at surface, I can sense 50 degrees Celsius. When I'm at 10 kilometer, there will be a difference of around 10 into 6.5 normal lapse rate, which means 65 degrees Celsius difference will be there at 10 kilometers. When I reach 20 kilometers, another 6.5 degree, that is a 65 will also be there, which means if I'm there at the tropopause of Sahara or tropical region or equatorial region, where the height of troposphere is maximum, I can sense maximum lapse rate there. Maximum lapse rate, if I round it the figure into 20 into 6.5 will be the value, which means there will be a difference of 130 degrees Celsius of temperature from the temperature of the surface, which means surface I have 50. Difference of 130 can be expected at the tropopause of the Sahara, which means 50 minus 130. The temperature will be minus 80 degrees Celsius will be the temperature at the tropical tropopause. Whereas I'm taking you to the polar tropopause, either Arctic or Antarctica, where the surface temperature is 0 degrees Celsius, where you have a height of around 6 kilometers in the polar region, height of troposphere. 6 kilometer height in the troposphere means 6 into 6.5. That is a normal lapse rate. 6 into 6.5 means that is around minus 39 or 40, minus 40. That will be the difference. So 40 difference will be there. 0 minus 40, minus 40 will be the value. So when I reaches the tropopause of polar region, I can sense minus 40. When I reach the tropopause of Sahara, I can record minus 80. This variation is based on because of the height difference in the tropopause. Fine. Next atmospheric layer is stratosphere. Stratosphere. The atmospheric layer lies beyond tropopause. Atmospheric layer lies beyond tropopause. Extends up to 50 kilometers beyond tropopause. Extend up to 50 kilometers. Maximum thickness at the poles, minimum thickness at the equator. Maximum thicknesses at the poles and minimum thickness at the equator, which means this is like this. This is the Earth. This is my tropopause, and this is my stratosphere, stratopause, which means here I have only 6 kilometers of troposphere. Rest of the areas up to 50 is a part of stratosphere. Here I have 18 kilometers of troposphere. The rest of the area is stratosphere up to 50, which means I have maximum height of troposphere at the equator, right? Because of maximum height, I have less space for the stratosphere. I have very minimal height for the troposphere in this polar region. Because of that, I have maximum thickness of stratosphere in the polar region, which means, in fact, the thickness of stratosphere is also controlled by the convection cells which is working in the troposphere. So the varying thickness of stratosphere is also controlled by the convection cells that are working in the troposphere. You write it, I'll explain it. The varying thickness of stratosphere is also controlled by the convection cells that are working in the troposphere. This varying thickness of stratosphere is also controlled by the convections, which means I have only this much of stratosphere at the tropical region because I have maximum height in the troposphere. Why I have maximum height at the troposphere in the equatorial area? Because I have maximum convection here. Suppose if the convection within the tropical area is limited, if the convection in the tropical area is limited, like this, I'll get some more space for stratosphere. Got it? And at the same time, if this convection cells in the polar region is extended bit like this, there will be a shrinkage in the stratospheric space in the polar stratosphere. So indirectly, the varying thickness of stratosphere is also controlled by the convection cells that are working in the troposphere. Within stratosphere, the first few kilometers, from 18 to 25, not exactly 18, 20 to 25. From 20 to 25, there is an isothermal condition exists. There is an isothermal condition exists, which means after troposphere drop of temperature, there is a temperature stagnation, and slowly the temperature will increase then. So this is what the isothermal area. From 20 to 25, there is an isothermal condition exists. After that, the temperature in the stratosphere increases slowly. Temperature in the stratosphere increases very slowly. This increase of temperature, with increase in altitude, is caused by this increase of temperature with increase in altitude is caused by the presence of ozone layer, and its photochemical action with ultraviolet radiation. The photochemical action with ultraviolet radiation, UV rays. So that is the source of heat. Which means it is not, don't write, which means it is not only the terrestrial radiation as the source of heating for the entire atmosphere. For troposphere, the terrestrial radiation is the source of heating. But the next layer, that is a stratosphere, there is a stratosphere itself is capable of heating themselves. Because of this action, that is a photochemical action. There is an ozone concentration is there, which absorb ultraviolet radiation, and there is a photochemical reaction is taking place in the stratosphere. They can heat stratosphere themselves. That is the reason why there is an increase of temperature with increase in height. But within the stratosphere, this rise of temperature is not very rapid. Once you enter into the stratosphere, very isothermal condition exists in the few kilometers. After that, very slowly the temperature increases because concentration of ozone attains in that height. There only heating is taking place. The lower part between 18 to 25, there is not much ozone is not present. Maximum concentration is beyond that. So that there is an increase of temperature is taking place beyond 25 kilometers. Fine. What is ozone layer? What is ozone layer? What is ozone layer? That's a function of ozone layer. What is it? Exactly. Within the stratosphere, there is around 25 to 30, 35. That is the area where you can expect maximum concentration of ozone. Ozone is an isotope of oxygen. It's an isotope of oxygen. It is largely concentrated in the 25, 35 or 50 kilometers of stratosphere. That is a region. And how it is created? Who creates it? The creation itself is done by ultraviolet radiation, UV rays. So let's see how ozone is created in the stratosphere. O3. UV radiation is consisting of UVA, UVB, and UVC. Among this, this guy is the harmful guy, UVB. Penetration of which can induce skin cancer, penetration of which can create problems in the life forms in the planet. Everything will be altered. UVB is the culprit. What about UVC? Ultraviolet radiation, UVC, is responsible for. Is there any issue with the color? Okay. Fine. Fine. So, this is a stratosphere. Ultraviolet radiation is penetrating like this. Oh my God. Oh, thank you. So, this is UVA. This is the Earth's surface. UVA can easily penetrate and reach the surface. There is no much problem. This is UVB. This is UVC. What is the impact of UVC is? UVC is completely absorbed in the stratosphere. There is no penetration of UVC into the troposphere. So ultraviolet radiation, UVA, B, C, is consisting of three streams, UVA, UVB, UVC. Within this, UVC is completely getting absorbed by the stratosphere, which means the oxygen molecules which are there in the stratosphere is capable of absorbing it. UVC. UVA is not harmful. They can easily penetrate into the troposphere. They can reach at the surface. And UVB is is the villain or it is the culprit. So how ozone layer is being created in the stratosphere, that is we are going to discuss right now. So let's see this. Within the stratosphere, there is a lot of oxygen molecules are there. Oxygen molecules are there. When ultraviolet radiation C comes, UV radiation comes, especially UVC, it causes the breakage of or a split of oxygen molecules into two oxygen atoms, which are highly reactive. They causes the split of two oxygen or one oxygen molecule into two oxygen atoms like this. They are highly reactive. So ultraviolet radiation penetrates stratosphere, find out the oxygen molecules there. It causes the breakage or a split of oxygen molecule into two oxygen atoms, OO. And since they are highly reactive, they will try to find some other oxygen molecules there. Club together, they results the formation of O3. This is how O3 is created. So ozone within the stratosphere is itself is a creation of ultraviolet radiation and its reaction with oxygen. This is how O3 is created. So we can write how is ozone produced. Ozone is being produced and destroyed all the times. Ozone is being produced and destroyed all the time. Ozone is being produced and destroyed all the time. Sun produces UVA, UVB and UVC variants. Sun produces UVA, UVB and UVC variants of ultra UVs. Sun produces UVA, UVB, UVC variants. When UVC reaches the stratosphere, it is completely absorbed by oxygen molecules and never reaches the surface and never reaches the Earth's surface. UVC splits oxygen molecules into oxygen atoms, These single atoms then react with These single atoms then react with other oxygen molecules, and result ozone. So these reactions increases the concentration of ozone in the stratosphere. Increases the concentration of ozone molecules. Next is, how does ozone protect us from UVB? How does ozone protect us from UVB? Ultraviolet B radiation. So ultraviolet A has reached the surface, no issues. Ultraviolet C is completely absorbed by the oxygen molecules in the stratosphere, and they create ozone layer. Right now within the stratosphere there is an ozone layer is created. Next, ozone absorb. This ozone layer, O3 absorb UVB radiation. When it reacts with UVB, the UVB radiation split O3 into one oxygen molecule and one oxygen atom. One oxygen molecule and one oxygen atom. By this photochemical action, UVB radiation will be neutralized. UVB will be neutralized or absorbed. Got it. This is how ozone layer is absorbing ultraviolet B radiation. And after that, what is the possibility? Next possibility, once UVB is neutralized, this oxygen molecule and highly reactive oxygen will combine together and they'll reform O3. This is how that cycle is going. Once O3 is joined again, they are capable of absorbing another UVB. Again, that causes a split. Again, they will join together likewise. So there is a cycle of UVB absorption, and there is a cycle of split like this. This is how it is happening. Then what is the threat here? How this ozone hole is being created? Not greenhouse gas. CFCs. Fine. So naturally, within the Earth's stratosphere, there is a cycle is running like this, a healthy cycle. Whatever UV radiation is penetrating, UVC is creating ozone molecules, and that ozone is capable of filtering the ultraviolet B radiation, which is very harmful. Once it is filtered, again they can rejoin and form ozone. So there is a healthy cycle will be running in the stratosphere. And when it is unhealthy, when it will become unhealthy, the thing is, the natural cycle is very balanced and it is capable of surviving there for billions of years. But within this natural cycle, if there is any human-induced action is done, that is the release of huge amount of CFCs, that can create some issues in the stratosphere. So, right, how do the chemicals deplete ozone? How do the chemicals deplete ozone? When a CFC molecule reaches stratosphere, when a CFC molecules reaches stratosphere, CFCs are normally ejected from deodorants, ejected from refrigerator, old refrigerators and all. So when it reaches in the stratosphere, it eventually absorb UV radiation. It eventually absorb UV radiation. CFC reaches the stratosphere, they eventually absorb ultraviolet radiation. It causes the decomposition of CFCs. It causes the decomposition of CFCs and release their chlorine atoms, chlorofluorocarbon. Within that, chlorine atoms will be released. Chlorine atoms releases its chlorine atoms. One chlorine atom can destroy up to how many ozone molecules? Any guess? Can guess? One chlorine atom can destroy up to? Yeah, it's your turn. Yeah. Too low. 1 lakh ozone molecules. 1 lakh ozone molecules. One chlorine atom can destroy 1 lakh ozone molecules. And too many of this chlorine bromine reactions and too many of this chlorine and bromine reactions disrupt the delicate chemical balance that maintains the ozone layer. Causing ozone to be destroyed, faster than it is created. That's all about ozone layer. So this is how ozone holes are appearing sometimes. And there is a protocol to curtail the usages of the CFC producing or ozone depleting substances. Log the usage of the ozone depleting substances. What is the name of the protocol? No. Montreal Protocol. Ban the ozone depleting usages of the ozone depleting substances. Montreal Protocol. In fact, this was one of the most successful treaties ever made in the history of human being. Montreal Protocols. It's regarding ozone depleting substances. The last point of today is the upper boundary of stratosphere is stratopause. Upper boundary of stratosphere is stratopause. So the next layer is mesosphere, then thermosphere, two small areas of the discussion. And after that, we'll be entering into incoming solar radiation, temperature, and atmospheric circulation. That will be the agenda of tomorrow's discussion. All right. Same time, right? All right. So any doubts? See you all tomorrow. Bye-bye. Both are the same. Both are the same. The thing is, air convection means it is a mechanism of transferring heat. Air is convecting or moving up and transferring that heat into the upper or higher altitude and coming back towards the surface. Yeah. So why the medium is air molecules. The medium of movement is air molecules, and what they are moving is the heat energy. The heat is convected upward means the heat energy is transferred upward due to the upward movement of the air convection. So I can travel to Chennai through flight. I can travel to Chennai through train. So here, what I am is I'm heat. I can be taken to Chennai through flight or through train. So here this molecules, air molecules are the mode of transportation. And that parcel they are parceling or taking towards the upper altitude is heat energy. They are just transferring agents, which means let's see this convection cells that are developing in the asthenosphere. There is radioactive elements are produced here. Radioactive disintegration is taking place. From here, huge amount of heat will be generated. That heat will be transferred towards the upper part of the asthenosphere, where the temperature is relatively low. So they are packing that heat from here. They are transferring that heat through that convection movement of magma. So that magma itself is moving and transferring the heat. Here within the Earth's atmosphere, this is the atmosphere. Earth's surface is heating that air column. They are taking that heat energy. They are moving by themselves for the transferring of heat. And once they release that heat into this much of area, they will become cooler. And once they are cooler, they will come back. Again, they will bring another batch of heat. They will transport it. So this is what the heat convection. This is what the air convection. Both are the same. Any other doubts?